So in exercise number 6, which will be also the last exercise for this week, we will solve an optimization problem, like a consumer optimization problem. I think we saw an exercise like this in the first problem set, which was dealing with the theoretical tools of public finance. And now we will look into like a similar model, but we will include taxation of interests and labor. And we will see that there will be some different effects when there are different effects when taxing labor income rather than interest rates. So consider a model in which individuals live for 2 periods and have utility functions of the form u equal to the log, so the natural log of C1 plus the natural log of C2. They earn income of $100 in the first period and save S to finance consumption in the second period. The interest rate is, so it's R and it's 10%. A, set up the individual's lifetime utility maximization problem, solve for the optimal C1, C2, and S. And then there is a hint, draw a graph showing the opportunity set. Okay, let me just go to a new page. So this is exercise number 6, and we are in A. So let me just again summarize the information that we have. So the utility function is log of C1 plus log of C2. Then what else do we have? We have, let's say income is Y and it's 100, so it's $100. RR is equal to 0.1, yeah, so 10%. So in A, we are asked to solve the utility maximization problem without any taxes. Yeah, so this will be an intertemporal optimization problem because the consumer is deciding on how much to consume today and how much to consume in the future. So the optimization problem is the following. So the consumer is maximizing over his consumption today, C1, and his consumption tomorrow, C2. And he's maximizing his utility, so the log of C1 plus the log of C2, such that, now comes the constraint, his consumption tomorrow is equal to his income, so 100, minus what he consumes today, C1. So this is actually equal to S. Yeah, so this is the savings basically, but I will not use the notation for savings because it doesn't actually matter. So just for you to know, so 100 minus C1, so income minus the consumption in period 1 is always the savings S. So the savings, so consumption in period 2 must be equal to the savings in period 1 times the interest rate that I'm getting on this. So it's times 1 plus 0.1. Okay, so this is the optimization problem. In the solutions that I will upload, I'm using a substitution method to solve this optimization problem. Here I will use the Lagrangian method. Yeah, so you have two different methods, and you can see the solution steps for any of the solution methods that you prefer. Yeah, so that's why I'm always trying to vary them. So let's write down the problem in Lagrangian form. So we are maximizing over C1, C2, and lambda, and we are maximizing the log of C1 plus the log of C2 plus lambda times, and now we can actually simplify the constraint just by factoring out everything. So what we then have is 110 minus 1.1 times C1 minus C2. Okay, so this is the optimization problem in Lagrangian form. And now we can we can write down the first order conditions. So first derivative is with respect to C1. And what do we have then? So the derivative of the log of C1 is 1 divided by C1. From this, we subtract lambda times 1.1. So then we have 1.1 times lambda. And this should be 0. If we rearrange this, we end up with 1 divided by C1 is equal to 1.1 times lambda. So we do the same thing for C2. So we take the partial derivative with respect to consumption in the future period. That's 1 divided by C2 minus 1 times lambda, so simply lambda. This is supposed to be 0. And if you rearrange this, we end up with 1 divided by C2 is equal to lambda. And the third partial derivative is with respect to the Lagrange parameter. So then we have 110 minus 1.1 times C1 minus C2, and this is supposed to be equal to 0. So what we need to find out now is the optimal ratio of consumption in the future period and consumption in the current period. So in order to find this out, what we simply do is we divide the first equation by the first order condition by the second first order condition by dividing each of the corresponding sides of the equations with each other. So I will write it down like this. I think I've shown you this kind of method before. So if we do this, what we have is C2 divided by C1 is equal to 1.1, and therefore what we get if we rearrange this is we get C2 is equal to 1.1 times C1. Okay, so for every unit of consumption in the first period, you consume 1.1 times this amount in the second period. Now, what we do next is we simply plug in this here into C2 here, and what we get, so then in 3, what we get is 110 minus 1.1 C1 minus 1.1 times C1. This is supposed to be equal to 0. And if you solve this, you get C1 star. So that's the optimal amount or the optimal consumption in the first period. And this is equal to 50. If we plug in 50 back into here, what we get is C2 star is equal to 55. So as a consequence, given this optimization problem, what the individual is consuming is 50 units in the first period and 55 units in the second period. And savings, so S star, will then be simply 100 minus C1 star, and that's simply equal to 50. So the individual will save 50 units, like 50 monetary units. There will be interest rate for this. I think it was 10%. So the income or the amount of money that the individual can consume in the second period is then 50 times 1.1. So it's then simply 52. And that's what we found here. Yeah. So this finishes the calculation part of the exercise. We still have to draw the opportunity set of the consumer. So that's also quite straightforward. So on the x-axis, we have C1. On the y-axis, we have C2. We have an income of 100. So if we fully consume everything in the first period, we can consume a maximum of 100 units. If we consume everything in the second period, we can consume a total of 110 units because we have an interest rate of 10%. And if we then connect those two lines, this is the opportunity set or the budget constraint. And we can even go further and to draw the solution into this coordinate system. So the solution would be here 55 And oh, this doesn't look good. Let me just change. So it's 55. And then, okay, this is again not precise, but then the solution be down here. So 55 and 50. There would be some kind of an indifference curve here, which would look somehow like this. And yeah, the solution is described as the point where the indifference curve representing your preferences over consumption today and consumption tomorrow is tangential to the opportunity set represented by the budget line. Okay, so this brings us to sub-exercise number 2. Now we have taxes. So now we have a government which is imposing a 20% tax on labor income. And again, we are asked to solve for the optimal levels of consumption and savings. And we are also asked to explain the differences between the new level of savings and the level that we found in sub-exercise A. And we are asked to relate this to the income and substitution effects. Okay, so the optimization problem this time will look a little bit different. So let me write this down. So now we are again maximizing over consumption today and tomorrow. The utility function doesn't change. It's still the same. But what changes is the budget constraint, because now we have taxes on labor income. And it will affect the budget constraint in the following way. So the consumption tomorrow is equal to the amount that we save in the first period. And now the income that we generate in the first period is $100, but we have to pay taxes on this, and the taxes are equal to 20%. So all that we have is 100 times 0.8. So that's our available income, labor income in the first period, our earnings. From this, we subtract the consumption, so C1, and it will be multiplied with 1 plus the tax rate, the interest rate that we have, so 0.1. Okay, and then this here again will be the savings. So this is S. So the only change that we had is that our income, which we generate in the first period, will be multiplied with 0.8 because the tax rate is 20%. In Lagrangian form, so the rest of the steps are quite similar to what we have been doing before. So now we are maximizing again over C1, C2, and lambda. We're maximizing our utility. Plus, and now if we again factor everything out, we end up with 88 minus 1.1 C1 minus C2. So that's the optimization problem in Lagrangian form. And now let us again start with the first order conditions. So really the steps here are analogous to the steps that we had before. So then we have 1 divided by C1 minus 1.1 times lambda. This is supposed to be equal to 0. Rearranging this, we get 1 divided by C1 is equal to 1.1 times lambda. Then again, taking the derivative with respect to consumption in the future period is then 1 divided by C2 minus lambda. This is supposed to be equal to 0. Rearranging this gives us 1 divided by C2 is equal to lambda. And as before, the third partial derivative with respect to the Lagrange multiplicator gives us 88 minus 1.1 times C1 minus C2 is supposed to be equal to 0. And now again, so I forgot to enumerate those conditions here. I'll just do it now. And now again, we divide the first order condition by the second one, so equation 1 divided by equation 2. Then what we get is C2 divided by C1 is equal to 1.1. Rearranging this, we get C2 is equal to 1.1 times C1. So what you can see now is that actually the optimal ratio between consumption tomorrow and consumption today did not change relative to what we had in the sub-exercise before, even though we have taxes now. And what you will see is that because the taxes are on labor rather than on interest rates, what will happen is that there is no substitution effect because the relative prices of consumption today and tomorrow do not change. And that's also the reason why this optimal ratio here is looking the same, yeah, as what we had in sub exercise A. The only thing that will change is that we have less income, so nominal income available, real income available, and we will only have an income effect. So now let's plug in um, again this expression here for C2 here, and what we get if we plug it in 3 is 88 minus 1.1 times C1 minus 1.1 times C1 is supposed to be equal to 0. Rearranging this, we get C1 star is equal to 40. And if you plug this into the, so if you plug in 40 again into the optimal ratio, what you get is C2 star is equal to 44. So this is the new bundle of, like the new optimal bundle of consumption in the first and the second period. And again, then savings are equal to 88 minus what we save, 88 minus what we save today. So it's 88 minus 40. So that's equal to 48. And what we were asked is, so what type of effects do we have here if we are if we have taxes on labor supply? So as I said before, there is no income effect here. So there is no, there is no substitution effect. So there is no substitution effect. I made a mistake there, sorry. Obviously, there is a mistake here. Of course, the income that we have is 80, not 88. So the savings is 80 minus the consumption today, so 40, and hence savings is equal to 40. Yeah, so just did a mistake there. Please correct this. But again, back to the other question that I asked. So there is no substitution effect since the relative price of consumption today and tomorrow does not change. There is only a income effect since our real income in the first period decreases. Yeah, so since the tax is only on labor income, it does not change the relative price of consuming today relative to consuming tomorrow. Hence, there is no substitution effect, and the only negative effect that we have is an income effect here. Hence, we have less real income due to this tax. And as a consequence, both consumption today and tomorrow simply decrease compared to sub-exercise A. This brings us to the last sub-exercise where now we have tax on interest income. So no tax on labor income anymore, but there is a tax on interest income. And then we are again asked to derive the solution for this case. And as you can already think, like a tax on interest income will change the relative price of consumption tomorrow and consumption today. So this is C. I will again write down the optimization problem. So again, we are maximizing over C1 and C2, and we are maximizing our utility. So here we see no changes. The thing which changes is again our budget constraint, because now consumption tomorrow must be equal to our savings, which is then again 100 minus C1. So since we have no labor tax anymore, our income that is available in the first period will be 100 again. So it's 100 minus C1. And to this we multiply the real interest rate that we have, so the net interest rate if we account for taxes. And this is then simply 1 plus 0.1 times 1 minus 0.2, because the tax rate is 20%, so it's 0.8. And this is the new optimization problem where we are paying taxes on interest rates. Not on interest rates, but on interest that we're getting. So if we now bring this into the Lagrangian form, we maximize over C1, C2, and lambda. So we maximize our utility. To this we add lambda times, and now if you factor out everything, you end up with 108 minus 1.08 times C1 minus C2. And now we simply follow the steps that we had in the previous sub exercises. So we take the partial derivative. This is equation number 1. So the partial derivative with respect to C1. This gives us 1 divided by C1 minus 1.08 times lambda. This is supposed to be equal to 0. Rearranging this gives us 1.C1 is equal to 1.08 times lambda. The second partial derivative with respect to C2 is then 1 divided by C2 minus C lambda. This should be equal to 0. Rearranging this gives us 1 divided by C2 is equal to lambda. And the third partial derivative is 108 minus 1.08 times C1 minus C2, and this should be 0. Dividing first order condition 1 by first order condition 2, we get the following. So we get C2 divided by C1 is equal to 1.08. And if we rearrange this, we get C2 is equal to 1.08 times C1. And as you can already see, this condition here is different than the condition that we had in the previous two sub-exercises. And the reason is simply because now the relative price of consumption tomorrow and consumption today changed, because since there is a tax on interest rates, consumption tomorrow becomes relatively more expensive than consumption today if we compare it to the previous sub-exercises. So before we had C2 being equal to 1.1 times C1. So for $1 of consumption in period 1, we would consume $1.1 in period 2. Now it's only $1.08. Yeah, so there is a reduction in consumption in the second period for every amount that we consume in the first period. Now again, if we plug this in to the third first order condition, we get 100. So in 3 gives us 108 minus 1.08 times C1 minus 1.08 times C1. This is supposed to be equal to 0. Now if you solve this, what you get is C1 star is equal to 50. And if you plug this back into this relation here, what you get is that C2 star is equal to 54. So what we had is that the consumption, so relative to sub-exercise A, the consumption in the first period stays the same. The reason for this is that here we have a income effect and a substitution effect. And for this type of utility function, the income effect and the substitution effect exactly cancel out. Therefore, there is no change with respect to consumption in the first period. But with respect to the consumption of the second period, what we find is that there is a decrease. I think there is a decrease of 1 unit. So we consume 1 unit less compared to sub-exercise A. And the reason is because there is a negative substitution effect in addition to the negative income effect. Sorry, the positive. So there is a negative substitution effect, and which is stronger than the income effect. So whatever sign the income effect has, it's stronger here. So the substitution effect, and as a consequence, we consume 1 unit less compared to sub-exercise A. And yeah, savings, I mean, it's also something that you can calculate. So the savings will be again 100 minus C1 star, and this will be equal to 50. And since we have to pay taxes on our interest, we cannot fully carry over the 10% of interests that we would get in the next period, but we only get 80% from this, which is then simply 4. So this is the reason why we then have a consumption of 54 in the second period. And yes, this finishes this week's problem set. So yeah, we will simply continue now with the chapters that you will see in the lectures. So next week I will not do another recap session, but I will continue with the problem set on chapter number 9, I think. Yeah. So see you next week.